Alright, so in this video, we're talking about something called a reaction coordinate. And a reaction coordinate is simply used to represent the amount of energy in a reaction. We've learned so far in class today that the amount of energy in a reaction is really important because it'll help decide whether or not a reaction will actually occur. So what we can do is model this in a graph. Now, when we create a reaction coordinate graph, usually we're going to have potential energy on our y-axis, and our x-axis is going to be the path of the reaction. Basically, this just tells us where we start and where we end in our reaction. So now what I've done is I've actually drawn in one of these reaction paths that we could be talking about. So this is usually the shape that our reaction paths are going to take, at least for the reactions we're looking at in this class. Now, if we look here a little bit closer, you can see that I've actually labeled the starting point here as our reactants and the ending point here as our products. This will always be true because with every reaction we're looking at, we're starting with our reactants and we are ending with our products. All right, so now that we know a little bit more about reactions and reaction coordinates, I've drawn for us a more specific reaction coordinate graph. Now you'll notice that this graph is more specific because I've labeled the sides here for my potential energy, and I've labeled them with a scale that goes by 10. Now this scale, or potential energy here, is measured in units called kilojoules. So when we look at reaction coordinates, we'll be talking about kilojoules. Now you'll also notice that the shape of my graph is very similar to what it was before. I start with my reactants, and I end with my products. Now, because I've labeled my scale on the side here, I can tell that my reactants start at 50 kilojoules. That means that the chemicals in their reactant form have a potential energy of 50 kilojoules. Now my products are lower on this scale. My products end up right here, which if we trace it back is about 20 kilojoules. That means that the potential energy of my products is 20 kilojoules. So over time, as I've moved along my reaction path, I've actually gone down in my potential energy, or potential energy has been lost from this reaction. Now you might be wondering why we don't just have a flat line. Why is our reaction coordinate curved like this? And really, it's curved because we often have to add energy to a reaction in order to get it started. For example, here, the highest point on our graph is about 80 kilojoules. That means that for our reactants to get to our products, we have to add some energy in order to allow that reaction to occur. You can almost think of it as a ball that starts here with your reactants, moves up as we add energy, and once it gets to this top point, it's willing to let the reaction go to completion and move on down to the products.